Oi, Sugarlump here, and in this episode, we will locate the PF of any parametric curve that exists out there. Last video, I related the evolute equation to the formation of these things called osculating circles, and included 3 visual examples of it in the episode. But there's one small issue. The episode is in Spanish, and I'm afraid my English-speaking viewers never got anything out of it, but no worries. There should be an English subtitle there to fix that. But just in case you haven't watched it, osculating circles are circles centered on the evolute and touches its corresponding point on the curve. Based on this, the equation of an osculating circle is derived from the general circle equation, where the parameters h and k are instead the x and y components of the evolute equation, and the r is simply the magnitude expressed by the second vector in that equation, which has this fancy 3/2 exponent on top of it. Now in this video, we will be relating the osculating circle to the process of locating the great parametric pseudo-focus. This process is similar to the one from the last series, but the approach of it is, in my opinion, much simpler than the last, and has a neat visualization to take away from. To remind you what it is, the PF is a point generally lurking under a peak or over a trough of a curve. If this peak or trough is bumpy, then this PF is close to the peak. But if the curve is flat or slowly undulates, this PF socially distances from the peak, distant from the curve. Other than that, the PF is also a point sitting on the tip or cusp of the curve's normal map or evolute, where it reaches its highest or lowest point on the graph. Since the PF is simply another point on the evolute, the PF is also considered a center of curvature. Since the pseudo-focus is a COC, there must exist an osculating circle that is centered at the PF. And hey, if the PF is a special kind of COC, what is so special about an osculating circle on the PF? Well, let's visualize that. Watch what happens when the circle skates along the evolute and approaches the peak. What can you notice? If you've guessed somewhere between the lines of the circle is the smallest when it approaches the pseudo-focus, then you're right. Because of this, we can then assume that the circle radius approaches its smallest value when the circle skates towards the pseudo-focus. Now what does this mean then for the circle equation? This means that the radius in that equation approaches a relative minimum value, and by finding the minimum value of the radius, we can determine a value of a, where the circle equation sits on the PF, or more directly, a value of a, where the evolute parameter yields the coordinates of the PF. With all this information, let's get our mathematical hands dirty. So our first objective is to find the minimum value of the radius expression in the circle. This expression in shorthand terms is written as x prime squared plus y prime squared to the power of 3/2 all over x prime y prime prime minus y prime x prime prime. Finding minima requires that we differentiate this expression and then equate it to 0. Since our expression is a fraction, we have to consult the quotient rule to prime this entire thing, where f is the numerator and g the denominator. But before we start taking the d of the expression, notice that we will equate some fraction to 0 after we differentiate. In the general case, equating quotient rule to 0 will simply make g squared cancel out, making our job of plugging in easier. And for a slight readjustment, let's move f prime g to the right and make it positive, leaving us with g prime f equals f prime g. After that, We then take care of the primes by evaluating the derivative of the num and then consecutively. For the numerator, we use chain rule by first differentiating this expression to the power rule. Doing so factors the 3/2 power to the expression and decrements its power to 1/2. Secondly, with the chain rule, we multiply this result by the derivative of that expression, where we do a chain rule again to both terms. Doing so will give us 2 times x prime times the derivative x prime prime plus 2 times y prime times the derivative y prime prime. This here serves as the numerator prime. Similarly, let us then prime the denominator. Since we are differentiating factors, we use product rule on each of these. For the first one, we will get x double prime y double prime plus x prime y triple prime. Then for the second one, we will get y double prime x double prime plus y prime x triple prime. After that, we simplify and get rid of these x prime prime y prime prime, leaving us with just x prime y triple prime minus y prime x triple prime for the denominator prime. With both our primes, we then plug the corresponding variables to the equation, where part by part, it looks like this. Next thing we do is simplify. What we do is take out a half power of x prime squared plus y prime squared from both sides, where the left one is reduced to power 1. After that, we multiply the 3/2 with a 2 times x prime prime plus 2 y prime prime. And that does just about it for simplification. So in the end, our minimum value equation is as follows: x prime y triple prime minus y prime x triple prime times x prime squared plus y prime squared equals 3 times x prime prime plus y prime prime times x prime prime minus y prime x prime prime. This equation here, folks, yields some solution which I'll call S, such that plugging S to the radius expression gives us its minimum value. And when a circle's radius is at its minimum, the circle's position or center also sits at the pseudo-focus. And since the circle's center is basically a point on the evolute, plugging S to the evolute parameter will immediately yield the coordinates of the parametric pseudo-focus. Let us now recap the entire process of locating the parametric pseudo-focus by establishing a new series of steps that directly lead us to the PF's coordinates. Given a parameter xt and yt, step 1. Find x prime t, x double prime t, x triple prime t, and y prime t, y double prime t, and y triple prime t. Number 2. Solve for t in the equation x prime t, y triple prime t, minus y prime t, x triple prime t, times the quantity x prime t squared plus y prime t squared, all equals 3 times x prime t, x double prime t, plus y prime t, y double prime t, times the quantity x prime t, y double prime t, minus y prime t, times x double prime t. Step 3. Plug the solutions in the parameter xt yt plus x prime t squared plus y prime t squared all over x prime t, y double prime t, minus y prime t, x double prime t, times the coordinate negative y prime t, x prime t. And these are the 3 steps that lead to the pseudo-focus of a parameter, which makes this our 3-step rule. Okay, so either you react because there are only 3 steps, or because each step is so compact that they'd be so tedious to work with, which means that time works against our favor when it comes to finding the pseudo-focus of this kind of curve. Even though finding the PF is work heavy, it's not gonna stop me from fitting an example in this video. And say we have a parameter where xt equals t squared minus t and yt equals t squared plus t. This parameter is one of the first examples I mentioned in this series, which is a parabola rotated 45 degrees clockwise. And it is this parabola we are finding the PF of. By intuition, you may already guess where this PF lurks on the curve, but it's also important to know the technical process when you're only given a parameter without a graph reference. So, let's get technical with this parameter, starting with step 1. Find the primes of xt and yt up to the third derivative. For xt and yt, the primes can be found by making use of the power rule 3 times. Thus, the consecutive derivatives of xt equals t squared minus t are as follows: 2t minus 1, 2, then 0. Similarly, the derivatives of yt equals t squared plus t are as follows: 2t plus 1, 2, and 0. Alright, with the derivatives, we now initiate step 2 and solve this weird equation. One can approach this step in many ways, so here's mine. Notice our triple primes are 0. If we just let the triple primes be 0 in this factor, we could see that the factor they reside into is essentially 0. Because of this, the entire left side just dissipates to 0, leaving us with 0 equals the entire right side. Since we are multiplying two things to equal 0, we make either factor equal 0 to satisfy the equation where x prime prime plus y prime equals 0, and x prime y prime minus y prime x prime equals 0. Alright, now we change these primes to the expressions we got, so we have these. Simplifying each equation, we will end up with an individual solution of t equals 0. And that does it for step 2. Moving on to step 3, we then plug the solution 0 to each t in the functions of the evolute equation. So as t equals 0, x of 0 equals 0, and y of 0 equals 0. Then, x prime 0 equals -1, y prime 0 equals 1. And then x double prime 0 equals 2, and y double prime 0 equals 2. With our acquired values, we then plug them into their corresponding functions, where we get 0, 0 plus 1 all over -1 times 2 minus 1 times 2 times the coordinate -1, -1. Doing the quick simplifications, we end up with 1/2, 1/2, and 1/2 acts as the pseudo-focus of our rotated parabola. In visual terms, 1/2 is the point just chilling over the parabolic trough, of which the osculating circle centered on it achieves the smallest size, and of which the evolute makes a sharp turn, which is what we expect from the good old pseudo-focus. That just does it about this video. Quite a long run, is it? We came from drawing circles to deriving a set of monster equations. I have some doubts that I may not muster the time and effort to do even one specific parameter to find a pseudo-focus of. But along the way, there will be some strategies to better help with locating that darn point we all yearn for. Thus, that's all for this video. See you next time. If you can ever mentally recover from this video,